Am I audible? Am I audible? Good evening to all. Welcome to the 4th week tutorial session of NPTEL Thermal Engineering Basic and Applied. My name is Ananthakrishnan. I am a PhD student from Department of Mechanical Engineering, IIT Delhi. I do this problem solving session as part of my PMRF TA duty. Before wasting our time, we can actually move to the contents. So this week we will be looking into the regenerative Rankine cycle, mainly the open and the closed feed water heater cycles. And we will look into a few multiple choice questions based on the regenerative cycle, as well as a few numericals as well. We can move into the question straight away. This is the first one. So look into the problem. It's regarding the efficiency of the ideal regenerative Rankine cycle. So whether it will be higher than that of a simple Rankine cycle, lower than that of a simple Rankine cycle, same as that of a simple Rankine cycle, always lower than that of the reheat cycle. Look into it. I'll also try to solve it in a couple of minutes. So have you looked into the problem? So what is the solution? Which out of the four options is the right one? So the question is, the efficiency of the ideal regenerative cycle is higher, lower, or same as that of simple Rankine cycle, always lower than that of a reheat cycle. So before going into the question, so we should be knowing what is the ideal regenerative cycle. So ideal regenerative cycle is basically the same Rankine cycle, but with slight modification, where part of the expanding steam at high temperature will be used to preheat the water in the boiler. So a part of the total heat input will be taken care by the expanding steam. But through this process, we might be compromising on the we might be compromising on the a total work output, but we are actually trying to reduce the overall heat input in this case. So if I try to draw that in the case of uh, a Rankine cycle, an ideal regenerative cycle, it will look somewhat like this in a TS plane. So if you start from the boiler output, so what happens is that it will consider an ideal process. It will expand in a turbine. So after a while, a portion of the steam will be bled out of the turbine, and this will be at a high pressure high turbine compared to the liquid that is pumped. So a portion of this will be mixed with the water which is condensed, that is available. I want a bit more better manner. So this doesn't make sense actually to draw like this. So yeah, this makes sense. So a portion of the steam will be bled after the expansion. So consider this to be process 1 and this to be process 2. And then it will be the portion of the steam that will be remaining after the bleeding, that will be condensed in the condenser. If you denote the portion of the steam, this as 1, this is the fraction y that will be bled out of the high pressure turbine, and then the remaining that will be expanded in a low pressure turbine, that will be remained as 1, that will be termed as 1 minus y. So that portion will be pumped, and these two mix together. Consider an open feed water heater where both the fluids will be mixing together, and then that will be mixing together and will be forming uh, a new state point 1, 2, 3, 4, 5, and from there onwards it will have a high pressure turbine, a high pressure pump that will be increasing the pressure to a high pressure, and then the boiler heating. So what happens is that uh, if there was no feed water heater, we should have taken it directly from this particular point to this particular point. So all the heat should have been provided by the boiler. But since we have used a feed water heater, a portion of the heat input will be taken care by a portion of the heat input will be taken care by the heat exchanger, or the heat and mass exchanger. Basically, a portion of the steam will be bled. So in this process, the total amount of heat input will be reduced. But if you look into the cycle as such, so the total heat input will be small, and then what happens is that in this next case, so if we were not considering a high pressure turbine, so what happened was that if sorry, a high pressure pump, if this particular unit was not there, then we should have actually gone for we should have actually gone for uh, heating from this particular point itself. So in that process, it would not have made a huge difference. But consider a pump work. Pump work is very negligible compared to that of the turbine work. So the actual heat input will be severely reduced in this process, because we need not lift it from this particular point to this particular point, only from here to here. So in that place, the total heat input will be reduced, but the total work will be slightly reduced, because we work per kg, in terms of work per kg, there would not be a huge difference, because even if it was not a feed water heater, we would have got uh, the expansion from 1 to 2. But the issue is that a fraction of the steam which undergoes expansion is different in both the cases. So in the original case, when there was no feed water heater, the expansion would have happened from 1 to 2 for the entire mass. So it will be H2 minus H1. But now the total work input will be uh, total work input will be 1 into this H1 minus this particular point. You can denote it by 2 dash. And from 2 dash to 2, the work input will be 1 minus the fraction of the steam that undergoes one work output will be 1 minus. So that is a difference. But if you look into the total, if you look into the total efficiency of the cycle, what we could see is that the total area of the cycle, at area under the cycle, that will be almost the same. Area under the cycle will be almost the same. So that means that the work output will be almost the same. Uh, Work output will be almost the same, but the work input will be slightly increased because another pump is also there. But in addition to that, there will be significant reduction in the heat input. So this particular term is most important. Since this is very less, the total amount of the total heat input will be less. Because of that, efficiency work divided by Q, when it reduces, efficiency decreases, assuming that work is not going to be affected that much. So in almost all the cases, what we could say is that the efficiency of the ideal regenerative cycle is higher than that of the simple Rankine cycle. There is also an additional way in which we can try to explain this. Efficiency could be denoted as 1 minus of T lower divided by T higher average. So since we are adding heat at a higher temperature, because this much portion is taken care by the feed water heater, so this increases, and correspondingly the efficiency also increases. So that is an alternative explanation to the efficiency consideration. So these two says that simple Rankine cycle efficiency will be higher than that of regenerative cycle. So other two options are wrong. It will be always lower than that of reheat cycle. No, can't say that because reheat cycle actually means that the exit of the turbine will be slightly more towards the vapor side. So it improves the quality. It doesn't always guarantee an increase in efficiency. So this is not right. So option 1 is right. That's the only solution. Now we can move to the second problem. Look into it. That's also a continuation of the first problem. The mean temperature of the heat addition of the regenerative cycle is same as that of the Rankine cycle. Is higher than that of the Rankine cycle, lower, none of the above, same, higher than that of the Rankine cycle. That is the explanation for the alternative way in which we have solved the first problem. Okay, then comes to the third problem. Coming to the third problem, in an open feed water heater, the extracted steam is allowed to mix with feed water. The feed water heater flows through tubes and steam is condensed outside. Steam flows inside the tubes and feed water outside. and both the steam and feed water flow inside two separate heat exchangers. That's straightforward. We have seen it in the first problem. The extracted steam is allowed to mix with feed water. So if there is a direct mixing between the feed water as well as the water which comes after the pumping. No, it doesn't have got any connection with the condenser side. It's basically the amount of steam that is extracted at the point 2 hash. So 2 dash, yeah. The process of extracting steam at a certain section of turbine to send to the feed water heater, it is known as I have explained, that's known as bleeding. Which of the following statements is correct? The temperature of the fluid entering the feed water heater is higher than that of the leaving fluid. The temperature of both the entering and the leaving fluid uh, is the same. Leaving fluid of the feed water heater is the same. The temperature of a fluid entering the feed water heater is lower than that of the leaving fluid. So this is slightly confusing. So what I meant to say is that, so if you consider the fluid that is entering at this particular point, a portion of the steam at a higher temperature will be condensing, and that process, that amount of energy, the enthalpy of vaporization will be transferred to the fluid, and that will be taking it up to this particular saturation conditions. So the temperature of this particular point will be same as that of the blood conditions, but that will be higher than that of the incoming fluid. So temperature 5 will be greater than temperature 4. So that is why I meant to say that the temperature of the fluid entering the feed water is higher than that of the leaving fluid. That's wrong. Temperature of the fluid entering the feed water heater is lower than that of the leaving fluid. So what I meant to say is that this particular temperature, these two mix together at this particular temperature. So the enthalpy of vaporization in this process, that will be delivered to increase the enthalpy of the pumped fluid. So T5 will be greater than T2. So to break the monotony, we can actually look into a few numerical type questions. Look into the problem. It's a numerical problem. Look into it. Consider a steam power plant operating on the ideal regenerative Rankine cycle with one open feed water heater. Steam enters a turbine at 15 megapascal and 600 degrees Celsius and is condensed in the condenser at a pressure of 10 kilopascal. Some steam leaves the turbine at a pressure of 1.2 megapascal and enters the open feed water heater. Determine the fraction of the steam extracted from the turbine, that Y fraction, and the thermal efficiency of the cycle. So it's a feed water heater. It's a continuation of all these problems that we have seen till now, but it's a numerical one trying to calculate the efficiency of the cycle. Look into it. I'll also try to solve. First of all, we have to draw a schematic and plot the same data points on the states on a TS plane, and then we try to solve it in an algorithmic manner. So we need to consider a steam power plant that operates. So that operates on an ideal regenerator Rankine cycle, and it is having an open feed water heater. Steam enters the turbine at 15 megapascal, 600 degrees Celsius, and is condensed in the condenser at 10 kilopascal. Fraction of the steam is bled from the high pressure turbine and goes into the open feed water heater, where the mixing of the high pressure, high temperature steam which condenses with and passes on the heat, as well as the mixes with the water which is being pressurized from the pump. So in this process, we need to find the extracted fraction of the steam as well as the thermal efficiency. So we will try to draw the schematic of the cycle, or regenerative Rankine cycle with open feed water heater. So we start from the low pressure turbine. So the low pressure pump, sorry, on a TS plane. Uh, so from 1 to 2, a low pressure pump mixes with the steam that is bled from the turbine, and then a high pressure pump to increase the pressure to the high pressure case, then a turbine, and then the boiler heating, then the turbine expansion. A portion of the steam will be bled, and then that's start from no, we can denote it at 1, 2. This particular point is 3, and this particular point 4. So this will be 5, 6, and 7. So this is an ideal representation saying that the steam condensed will be at the saturated condition. The steam extracted will be at the saturated condition, which need not be. So in many cases, this particular thing can be outside the vapor dome as well. So in that case, it will be the process will be looking like this. So this will be the boiler 5, 6, and then next and it mixes to 3, and then goes down. So it can be definitely this as well, where the uh, vapor dome, this will be the vapor dome. So it can definitely take this form as well. So then the vapor dome will become like this, and it goes. It can go inside this as well, and then okay, it can take this kind of a route. Sorry for the poor drawing skills. So this is a case of open feed water heater. base regenerative Rankine cycle. So if I try to draw a schematic of the whole process, it will look somewhat like this. We can start from point 1. So there will be a pump, a low pressure pump, and we are being given the pressure is 10 kilopascal in the condenser. So the starting pressure will be 10 kilopascal saturated pressure, saturated liquid pressure, and from there uh, pumping, it will be reaching the point 2, and it will be at the same pressure as that of the pressure that is been expanded. It's a constant pressure process, basically this whole heat exchange process in 2, 3, and 6. The process 2 will be at the same pressure, 1.2 megapascal. So this pressure is 1.2 megapascal. So that is given. And then it will be fed into the open feed water heater, where a portion of this will be water and the other portion will be coming from point 6 or say it as 0.6. Yeah. This will be coming from 6, that is a vapor, and the 6 and 2 mixes together to give the point 3. The point 3 will be at 1.2 megapascal, same pressure. Point 6 also will be at 1.2 megapascal. We do not know anything about the temperature as of now, but it will be a saturated condition. You can easily get from the steam table. So 1.2 megapascal you'll get, then uh, 7. Yeah. So this particular point will be 1.2 megapascal, and that will be the mixed condition of 6 and 2, and from there it will enter into a high pressure pump, and it will be at point 4. And that will be at a pressure of 15 megapascal, and then a boiler to input, and then exit of the boiler will be at point 5, and it will be fed into a high pressure turbine. And that is work turbine out. So this will be the pump input in these two cases, and then it will be a portion of the steam will be bled out of it. That fraction will be y, and the 1 minus y will be going out and will be expanded continuously, and it will be going out to the condenser to the 10 kilopascal. So this will be at state point 7, and then there will be the condenser heat exchanger, and this will be the Q out portion, and then it will be fed back to the pump saturated condition. Okay, now that's done. Condenser Q out pump will be the work input cases. heat input will be in the boiler, and this will be the open feed water heater, where both heat as well as mass exchanging take place between the high pressure, high temperature steam and the low pressure pumped fluid, and there will be proper mixing and it will be coming out. Now we can try to approach it in an algorithmic manner to find the steam extracted fraction, that is Y, and then so this is, if it is 1, this is Y, and this will be 1 minus Y. So that is there. Now so that is there, and now we have to solve uh, all the state points, and we will arrive at the final efficiency as well as the extracted steam fraction. So first of all, we start with the starting point, that is point 1. State point 1, state point 1. State point 1. So the pressure will be P1 will be 10 kilopascal. So, and the condition will be, it will be saturated liquid. So this particular point, that will be saturated liquid. So from the steam table, we can get the enthalpy, the saturated liquid enthalpy at 10 kilopascal. So that will be equal to 191.81 kilojoule per kilogram. And the corresponding specific volume will be the saturated fluid volume at 10 kilopascal. So that will be equal to 0.00101 meter cube per kg. So these 2 points we'll get straight away. Now we can move to the second point. So state point 2, will be at the pressure of 1.2 megapascal, and so just like the previous week where we have seen the work input to the pump could be represented in terms of the specific volume and the changing pressure, and from that we can actually arrive at the second point's enthalpy. So we can couple these two equations to find the second point's enthalpy. So work done in the pump 1, so we can denote it as pump A, and this is pump B. So it will be work done in the pump A will be equal to the new 1 into P2 minus P1, the specific volume. At the point 1, we since this is a pumping process and not a compressing process, we assume that there will not be a change in volume. There will not be a significant change in volume. It will be very minute. So we can assume that the starting and the ending of the pump will be having the almost the same specific volume. And it will be equal to 0.00101 into P2 will be, the second pressure will be 1200 kilopascal minus P1 will be equal to 10 kilopascal. This is 1.2 megapascal, so 1200 kilopascal. So that will give us the total work that will be equal to 1.2 kilojoule per kilogram specific work. And from here we can denote it as work done in pump A will be equal to H2 minus H1, and from there H2 will be equal to 191.8 plus 1.2, that will be equal to 193 kilojoule per kilogram. So that is there. So state point 1 and state point 2 we obtained, and now we can actually move into the state point 3, that is the mixing of the point 6 and point 2. But currently we do not know. But we consider that the entire steam that is bled from point 6 will be condensing and will be mixed with the point 2 to get the point 5. 0.3. So the state point 3 will be the saturated liquid condition at the pressure of 1.2 megapascal, the same pressure. This is a constant pressure process, so that will be 1.2 megapascal. Uh, and uh, and straight away we can obtain from the steam table. So P3 is given as 1.2 megapascal. So the saturated liquid U3 will be equal to 0.001138 meter cube per kg. H3 will be 798.33 kilojoule per kilogram. This is from the steam table. So we can obtain the state point 3 straight away. Now we can move to the state point 4, the exit of this pump. Just like the state point 2, we can obtain the new and from there we can obtain everything straight away. So the state point 4 P4 will be 15 megapascal, and that will be the second pressure. The third pressure, basically from second to the third, state point 3 to state point 4. So work similar to the previous case, work done in the pump B could be written as nu3 into P4 minus P3. So that will be equal to 0.001138 into P4 will be 15 megapascal. So 15,000 minus 1.2 megapascal will be 1,200. So it will give us 15.7 kilojoule per kilogram. So if you compare the magnitude between these and the other enthalpy differences, it will be very minimal. So here it is just 15, and the possible enthalpy difference in the case of turbine would be amounting to close to thousands. So therefore, H4 will be equal to H3 plus Newton in pump second. So basically H4 will be 798.33 plus 15.7 equal to 18814.03 kilojoule per kilogram. So we get to see state point 4 as well. So left hand side is done. So we know all the state point 4. Now we move to the right hand side. So just like the same approach, state point 5 will be the exit of state point 5 will be this particular point. It will be at 15 megapascal and 600 degrees Celsius. It's a superheated condition. P5 will be 15 megapascal and T5 will be 600 degrees Celsius. So corresponding to superheated steam, H5 will be equal to 3583.1 kilojoule per kilogram, and S5 will be 6.6796 kilojoule per kilogram. So that is when, and state point 6, we do not know. So we initially had drawn in such a way that this will be meeting the saturated vapor condition, but it need not be. It can be very well outside this vapor dome as well. It can move away from the vapor dome, and this can take this kind of a form. So this will extend towards the right and then come down like this, and then go into a constant pressure process in the feed water heater that can take that form as well. So we do not know currently, so we have to look into the same method that we have applied in the previous case, where we calculate the entropy at state point 5 and say that the state point 5 and state point 6 will be having the same entropies, and then solve it accordingly. So state point 6 will be having the same entropy as that of state point 5. So that will be 6.6796 kilojoule per kilogram Kelvin. And the we know the pressure will be P7 will be sorry, P6 will be 1.2 megapascal. So from the steam table we can see that this will be a superheated region, So our assumption, initial assumption that it might be at the this particular state point, saturated fluid, saturated vapor state point might not be right. So it will be like this. So this is the correct diagram. So state point so this is the wrong diagram and this is the right diagram. So wrong state point. Wrong state point 6. So it will be the superheated region and the enthalpy will be equal to H6 equal to 2860.2 kilojoule per kilogram. So basically we see at 1.2 megapascal what will be the saturated vapors enthalpy, and if this enthalpy is greater than that, it will be obviously a superheated condition. That is a check that we have to do from a steam table. Now we can move to the state point 7. Will be the exit condition of the turbine. So S7 will be same as that of S5. It's an ideal regenerative Rankine cycle. So it's a isentropic process. S7 will be same as at S5, and we know that the pressure will be 10 kilopascal. So it might be inside the vapor dome. So we have to find the quality. So based on that, we calculate X7 will be equal to S7 minus S, the entropy of the entropy of the saturated fluid at 10 kilopascal divided by the entropy change at 10 kilopascal. So the entropy change for the condensation process at 10 kilopascal. So condensation of vaporization for 10 kilopascal. So these two we can obtain from the steam table itself straight away. So it will be equal to 6.96 minus 0.6492 divided by 7.499. So it will be the quality of the steam will be equal to quality of the steam at the exit of the turbine. Exit of the turbine will be 0.8041. So we get to see this quality, and from there we can get H7. H7 will be equal to same approach. H7 will be equal to H fluid at 10 kilopascal plus X7 into HFG at 10 kilopascal. That will be 191.81 plus 0.8041 into 2392.1. So that will be equal to 2115.3 kilojoule per kilogram. So that completes almost all the state points. Now, the first part of the problem, we need to determine the fraction of the steam that will be bled from 0.6. So basically we need to calculate what is Y. For that, we need to use the energy balance in the open feed water heater. So whatever comes inside mixes with the whatever which is coming, whatever comes from the turbine mixes with the fluid which comes from the pump and goes outside at 1.2. We know all the energies at the input and the output, also the mass as well. So we can use this continuity equation as well as the energy balance to, or the mass continuity and the energy balance to get the fraction of the steam. So if fraction of steam fraction of steam that is bled from the turbine is Y. So basically, if I draw the open feed water heater, a portion that comes from pump that is 1 minus Y, and the portion that is coming from the turbine that is Y mixes together to give, this is 0.6, mixes together to give total 1 Y plus 1 minus Y, it will be Y, it will be 1. So energy balance is y into H6 plus 1 minus y into H2 will be equal to H3. We know every term, so y will be equal to just rearranging the terms and we'll get H3 minus H2 divided by H6 minus simplification, mathematics simplification. Substituting the value of H3, we have calculated H3 to be 798.33 minus 193.01, that is H2, that is pump output of the low pressure pump. 193 divided by 2860.2 minus 193. So H6 already we have calculated from the previous case, that is 2860.2. And then we'll get the fraction of the y will be equal to 0.227. So 22% of the steam that is entering the turbine will be bled to in the feed water heater. That is the first part of the problem. Now we can tackle the second part. So we need to calculate the efficiency of the cycle. So that will be equal to, efficiency will be equal to work net divided by Q in. So it will be equal to 1 minus of Q out by Q in. So these two are the same. So Q out will be a fraction of the steam that will be going into the condenser, that will be 1 minus y. And the heat input will be from 4 to 5 in the boiler. That will be the total mass of the steam. So Q out will be equal to 1 minus V, the fraction of the steam condensing completely, condensing 1 minus Y into H7 minus H1. H7 minus H1 straightforward. We know every terms 1 minus 0.227 into 2115.3 minus 190.81, that will be equal to 1486.9 kilojoule per kilogram. So the Q out will be this much, and the Q in will be equal to H5 minus H4. That will be equal to 3583.1. So H5 will be the heat input. That will be the steam output. The steam input to the turbine condition H5 minus steam input to the boiler, that is H4. So H5 will be 3583.1 and H4 will be 814.03. It will be 2791 kilojoule per kilogram. Therefore, the efficiency will be equal to 1 minus of Q out divided by Q in. Substituting the values, it will be 1 minus 1486.9 divided by 2769.1. That will be 46.3%. So we could see this is a case of a regenerative Rankine cycle with open feed water heater, and its efficiency is still not even 50%. It's 46.3. So if you try to compare it with a Rankine cycle that operates within the same Carnot cycle that operates within the same thermodynamic limit, so efficiency of a Carnot cycle will be equal to 1 minus of T low by T high. So T low will be low temperature. The high temperature will be 600 degrees Celsius, and the lowest point will be the saturation temperature corresponding to 10 kilopascal. So that will be 1 minus of So corresponding to 10 kilopascal, we need to calculate the saturation temperature condition. So that will be equal to 45.81 degrees Celsius. So that will be equal to 273 plus 45. So that will be equal to 318 Kelvin divided by the temperature at the highest operating temperature will be 600 degrees Celsius. So that will be 873 Kelvin. So basically, that will be equal to 373 divided by 870 Kelvin. 8 divided by 873.36. So that will be equal to the efficiency will become point close to 63.6%. So the maximum possible efficiency from the Carnot cycle will be somewhere around 63.7%. That is a maximum attainable. And we using these kind of slight tweaking to the model, just like the regenerative cycle, we are trying to improve the total efficiency to reach the same 63%. It's not possible because irreversibilities are involved in the case of these type of cycles. That is, in Carnot cycle, it's a completely reversible cycle, so we ignore all the irreversibility parts. So that is a theoretical possible maximum. But so we are actually trying to maximize the efficiency that we get through these kind of small tweaks. So this efficiency is 46, and this is greater than that of a simple Rankine cycle that we have seen in the previous cycle, previous week. So it was somewhere around 40 IS. So we'll look into another problem. This is an open feed water heater. The other one is a closed feed water heater, and try to gauge what will be the difference in the efficiency that the closed feed water heater can attain in comparing to the open feed water heater. So this is the next problem. Consider a steam power plant that operates on an ideal reheat regenerative Rankine cycle with one open feed water heater, one closed feed water heater, and one preheater. Steam enters a turbine at 15 megapascal and 600 degrees Celsius and is condensed in the condenser at a pressure of 10 kilopascal. Some steam is extracted from the turbine at 4 megapascal for the closed feed water heater, and the remaining steam is reheated at the same pressure to 600 degrees Celsius. The extracted steam is completely condensed in the heater and is pumped to 15 megapascal before it mixes with the feed water at the same pressure. Steam for the open feed water heater is extracted from the low pressure turbine at a pressure of 0.5 megapascal. Determine the fractions of the steam as well as the thermal efficiency of the cycle. So this has got a couple of feed water heaters, one open and one closed, and we'll see it's operating at the it's operating between the same temperature limits. So we will see what will be the change in efficiency that an additional closed water heater can bring into the table. Try to look into the problem. I'll also try to solve within a minute. So this is a continuation of the previous problem. It will be having an additional term of a closed feed water heater. So this means that the fluid will not be mixing in the closed feed water heater. It will be exchanging heat. So this is actually a method using a closed feed water heater before an open feed water heater to improve the efficiency of the cycle. So what we are trying to do is trying to minimize the total amount of heat input. We are trying to reduce it as much as we could. So in that process, we will be compromising the heat, the work output as well, but we will be reaching a we'll be reaching a trade-off where the input heat reduction will be same as that of the input the work output. So we'll be reaching a maximum point of efficiency that is attainable using this kind of a system. But we are having a simultaneous reheating as well in this process. So we'll see how much the efficiency will increase in the cycle. So before going into the problem, we will just draw the schematic and as well as the cycle. So on a TS plane, we can draw it, and simultaneously the schematic also we can draw. There was a pump, a low pressure pump, just like the previous case, which operates at 10 kilopascal. Starting will be 1, starting point will be 1, ending point will be 2, and it will be 10 kilopascal. And from there, it will be moving to a open feed water heater where the fluid will be mixed. The fluid will be mixed so at a lower pressure, basically at a lower pressure, it will be mixing with the steam coming at 0.5 megapascal. So it's an open feed water heater, and so this is open feed water heater, and this will be mixing with a low pressure steam at zero point 0.5 extracted at 0.5 megapascal. So we do not know that point particularly right now. So we'll leave it there itself. So open feed water heater, and the mixed fluid will be at mixed fluid will be at 0.5 megapascal. So that particular point will be state point 3. From there, it will be pumped again, pump B, to higher pressure. So that is in between pressure, that is 15 megapascal. That is actually 4 megapascal. So this will be at 4 megapascal. And from there, it will be mixed with the high pressure steam extracted into a closed feed water heater. Closed feed water heater. So since this is a closed feed water heater, there will be only heat exchange in this process. So there will be a portion that will be going inside, and then it will be coming out at, say, there will be 2 input and 2 output. So since this is a closed feed water heater, there will be heat exchange that's happening. So 4 will come out at a point. 4 will come out at a point of 6 and no, so it will be heated in that process. 4 will be coming at a 0.5, and then there is this The other side will be having this particular fluid will be heated up with a high pressure steam that comes at say high pressure basically that will be 4 megapascal. And then that will be condensing in the process and it will be reaching the saturated liquid condition at the 4 megapascal. So we can denote that particular point as 6.6. And then we will be having two steams. One will be at 6, the same pressure, saturated liquid, and then other that will be at the pressure 4 megapascal, uh, and but it will be heated. So that will be at 0.5. So now we need to mix both of them, 5 and 6. So before that, the 0.5 will be at 4 megapascal, and 4 megapascal, and a point pump B should be also the fluid which is coming out of the pump B should also be at the same pressure. So basically there is slight bit of confusion because this will come at 4 megapascal and it will become saturated liquid at 4 megapascal. And if it has to be mixed, both of them should be at the same pressure. So and the final pressure should be same as that of 15 megapascal. So it has to be fed into the boiler. So in this case, there's a slight confusion. So pump B actually doesn't uh, pump B actually doesn't increase it to 4, but rather it increases to 10 megapascal. So this is a closed feed water heater. Closed feed water heater. So there is only the heat that will be transferred from the upper fluid to the lower fluid. So the pressure remains the same through. So this will be at 10 megapascal. Sorry, that will be at 15 megapascal. I beg your pardon. That's 15 megapascal. The high pressure in the boiler. That will be 15 megapascal. So this will be at 15 megapascal straight away, and this will be at 4 megapascal, but that needs to be pressurized. This liquid needs to be, this will be condensing and it will become saturated liquid, and that needs to be pressurized. So this goes inside a pump C, and it will be pressurized to the same pressure 15 megapascal. So so that particular point we can denote it by 0.7, and then these two fluids mix in a mixer and gives us 0.8. That is the input to the boiler. And then that will be taking in the heat. So boiler going into the boiler, and then at the exit of the boiler there will be a portion that will be going into the high pressure turbine. So there is this high pressure turbine, and a portion of that steam will be bled, and then there will be a reheating. So it is mentioned that after the steam is extracted at 4 megapascal, the remaining the remaining steam is reheated to the same pressure at 600 degrees Celsius. So 4 megapascal to 600 degrees Celsius. So a portion of that will be going into the boiler again. So this can be quite confusing. So I'll draw a boiler 2 separately, and then it comes out of it. And so I forgot to add a few state points. So 8, it will be 9, high pressure turbine, exit of the high pressure turbine, that will be at 11. That will be bled to the close to feed water heater. And then the exit of the high pressure turbine will be 12, and the boiler heating. Uh, I beg your pardon. So these 2 points would be actually same. The exit of the high pressure turbine before it enters the boiler, both of them will be at the state point 11. I beg your pardon. The both of them will be at the state point 10. State point 10. So both of them will be at state point 10, and then this will be also at state point 10. This will become more clear while I try to draw it in a TS diagram. So 10, it goes into the boiler, gets heated up and become 11. And from there, it undergoes a low pressure turbine expansion. Low pressure turbine expansion. That is state point 12. And from there, a portion of the steam will be bled to the open feed water heater at 0.5 megapascal, and the remaining goes into the remaining just expands in the low pressure turbine, and then it reaches state point 13 and condenses in the condenser, uh, and goes into the pump state point 1. So this might look a bit confusing. I can draw it in a better manner, but this will become more clear while I try to plot it in a TS plane. Post feed water heater. So we have 4 megapascal, and then post feed water heater. So writing this might, I can denote it as CFWH. CFWH. So I'll try to draw the same on a TS plane. So starting from point 1, so this will be 1 to 2 constant pressure isentropy process, pumping process 1 to 2 from 10 kilopascal, from 10 kilopascal to 0.5 megapascal. So and then it moves into an open feed water heater where it mixes with a fluid and comes at this particular point, the total fluid. So basically we do not know where the exit, where the input, where the steam will be bled from, but we know the total pressure that is present in the open feed water heater on the higher side, that is 0.5 megapascal. So we can denote it like this. So we assume that this is still the input, the point from where it will be extracted is still out, uh, just in the vicinity or outside of the vapor dome. So we mix both of them, and it comes from state point 12 at 0.5 megapascal. It mixes and gives the uh, state point 3. So and from there, uh, it will be the second pump will be pressurizing it to 15 megapascal, and that state point will be state point 4. And there is a closed feed water heater. There is a closed feed water heater just immediately after this. So what happens is, let's not draw the vapor uh, dome right now. It can actually create a bit of confusion. So I'll draw it after drawing this, but to show that it might appear like this. Uh, okay, it will be better. Okay, the second one will be better, I guess. So from a state point 4, it will be there will be a open feed water heater. There's a closed feed water heater. Basically, the steam that will be extracted uh, at a pressure of 4 megapascal. It will be extracted maybe at 4 megapascal somewhere at this particular point. We do not know that point, but currently we have denoted as point number 10. So you assume that this is point number 10. From there, a portion of the steam will be bled and will be heating up the heating up uh, the the pumped fluid, which is at a 15 megapascal. So because of that, the pumped fluid will be increasing its temperature to it will be reaching the state point 5. Uh, State point 5, and this will be condensing and will be reaching the state point 6, this particular point. So 5 and 6, but 6 will be at lower pressure at a 4 megapascal. So it needs to be pumped to the same pressure. So it will be pumped to the same 15 megapascal. And then and uh, So basically, 4 megapascal, it will be pumped to the same pressure. So that particular point will be 0.7, and then there will be a mixer where the 0.5 and 0.7 will mix together to give 0.8. So that can have that actually slightly confusing. I'll use a different pen color to show that particular where exactly that point would be coming in. So so it will be a straight line like this. Okay, 4, and the state point 5 will be somewhere around this, and the state point 7 will be somewhere here. So the state point 8 will be a combination of 4 and 5 and 6. So it will be coming somewhere around in between here. So the entire fluid will be at the state point 8. So this will be the state point 8. Say. And from 8, it will be boiled to state point 9. And from 9, a high pressure turbine will be there, and it will be expanded to point 10. And from there, a portion of the steam will be bled back into the open closed feed water heater, and the remaining will be reheated back to state point 11. And from there, 11, uh, it will be expanded in the low pressure turbine. A portion of the steam will be bled at 0.5 megapascal, and the remaining part will be expanded completely in the low pressure turbine. And the exit point will be 0.13. So this top pressure will be 15 megapascal. So this itself has taken quite a bit of time to arrive at the actual schematic as well as the TS plot of a steam power plant that operates on an ideal preheat regenerative cycle. So basically, what happens is that the pumped fluid will be heated in an open feed water heater, mixes and reaches a 0.3, and then it will be pressurized to the final pressure 50 megapascal, and and it will be reheated, and it will be heated up to 0.5 by using the steam bled at an intermediate pressure, and they will be this heat exchange process will be happening in a closed feed water heater, the second one. And after that, there will be two different streams. One will be at a higher pressure, one will be at a lower pressure. You have to use a high pressure pump to pump the water that will be condensed after coming from the uh, after being bled from the intermediate uh, point, and then it reaches 0.7, and these 5 and 7 mixes each other to reach 0.8, that is an intermediate point of the temperature at the constant pressure. So the actual boiling process takes place from 8 to 9, and the other side 9 to 10 will be high pressure expansion. A portion of that will be bled in an intermediate pressure to a closed feed water heater, and then the remaining will be reheated to the it will be reheated to the same temperature. So it will the point 11 will be same as at 600 degrees Celsius, and from there another low pressure a portion of that steam will be bled in a low pressure uh, turbine. Portion of the steam will be bled in a low pressure turbine, and then that will be going into the open feed water heater, and then the remaining will be expanded into a condenser. Expanded, and it will be rigidly heating the condenser. So we need to allocate the portion of the steam that goes from one side to the another. If you consider the total fluid in the high pressure turbine as well as the boiler is 1, the portion that goes into the closed feed water heater is Y. The remaining steam is 1 minus 5, uh, 1 minus 5 here and here, and then another fraction of the steam Z that goes into the open feed water heater. The fraction of the steam that will be expanded remaining is 1 minus Y minus Z, and the same 1 minus 1 minus Y minus Z will be here as well, and it will be mixing with the Z to give 1 minus Y, and it will be mixing here somewhere here to give the Y. So that Okay, so that is a schematic, and we'll try to approach it just like the previous way, in a in an algorithmic manner, and it's straightforward actually. We need to determine the state points, and we try to solve it just like the previous case. Here, an additional component of the closed field water heater will also be there. That's only difference. We will try to tackle it in a stepwise manner, and it's a straightforward problem. So we can try to solve it straight away. So in this case, So we start from the point 1, state point 1. So that will be the saturated liquid at 10 kilopascal. So we have already seen in the previous question. So that will be 191.81 kilojoule per kilogram. And the point 2. So there's an intermediate pressure of 0.5 megapascal. So in the previous problem, this was at 1.2 megapascal. So that was a completely different pressure. Here we have two intermediate pressures. One is 4 megapascal and the second one is 0.5 megapascal. So H2 we have to calculate based on the specific volume at the point 1 as well as the pressure difference. So that will be equal to specific volume at point 1 into P2 minus P1. So specific volume at point 1, it's the same as that of the previous case. That will be 0.0 0.00101 0.00101 multiplied by the higher pressure will be 0.5 megapascal. So that will be equal to 500 kilopascal minus the starting pressure will be 10. So 490 into 0.001. That will be equal to this is the work in the pump. Sorry, there was a mistake. Work in the pump. So that will be somewhere around 490 into 0.001. Basically 0.49 kilojoule per kilogram. Therefore, H2 will be equal to WP plus H1. So that will be equal to very nearby. That will be 192.3 kilojoule per kilogram. So basically 0.59, 0.49 plus 199.81. So we will get the points 3.2 as well. Now we move to the state point 3. State point 3 is the mixing enthalpy of in the open feed water heater of 0.2 and 0.12. So basically state point 3 is the saturated liquid at 0.5 megapascal. So that enthalpy will be equal to 640.09 kilojoule per kilogram. And state point 4 will be the high pressure pump, the intermediate pump. So that will be giving work done H4 just like the previous case. Work done in the pump A, B will be equal to nu2 into nu3 into P4 minus P3. So P4, P3 will be equal to 15 megapascal. P4 will be 15 megapascal, and P3 will be equal to P3 will be equal to the 0.5 megapascal. So difference will be equal to 14.5 into 10 cube kilopascal multiplied by the new 0.001. That will be giving you the work. So it will be somewhere around 14.5, and correspondingly the H4 will be equal to H3 plus this particular quantity 640 plus this particular one. this will be equal to 643.9 kilojoule per kilogram. So H4 we have determined, and then state point 5 will be equal to so we have to take into consideration one important thing in this case. So this is an ideal reheat regenerative cycle. So this particular point 5 will be at the same temperature as that of point 6. So basically point 5 will be same as at a point 6. So that is one important thing that we need to identify while solving the ideal regenerative reheat cycle. So point 5 enthalpy will be equal to so at T5 is equal to T6 at the same saturated temperature, we'll get at pressure is equal to 15 megapascal. We'll get the enthalpy of 1087.4 kilojoule per kilogram. So in this particular case, we can actually kind of ignore the enthalpy difference between these two state points as the temperature as the entropy difference is very less between both of them. So H5 we can, H6 we can approximate to that of H5, that is equal to 1087.4 kilojoule per kilogram, and state point 7 will be the confluence point. The enthalpy the state point 7 will be this particular point where the condensed liquid will be pressurized up to. So it's 15 megapascal, and at the same specific volume as that of specific volume of 7 will be same as that of specific volume of 6. So based on that, we can say H7 will be equal to H6 plus, just like the previous case, the pump work we have to take into consideration, plus U6 into 15 megapascal, 15 megapascal minus 4 megapascal. 4 megapascal. So that will be coming around 1101.2 kilojoule per kilogram. On the right hand side, similarly, so an additional term H8 is there, but this has to come from the enthalpy balance of the mixer. And on the right hand side, it will be H9 will be 15 megapascal and 600 degrees Celsius, and we can solve it same in the same manner. State point 9 H9 will be uh, 600 degrees Celsius and 15 megapascal. So we have already determined in the previous case H9 will be equal to this H5 3583.1. Three five eight three 0.9 kilojoule per kilogram corresponding to superheated steam at 15 megapascal and 600 degrees Celsius. So it's a bit tiresome because we have to substitute all the values at all these points, and then state point 10 just having the same entropy as that of state point 9 and state point 9, uh, but will be at 4 megapascal. So based on that, we'll be getting the state point enthalpy as 3155 kilojoule per kilogram. Similarly, H11 uh, will be at 4 megapascal and 600 degrees Celsius. You look into the steam, look into the steam table at 4 megapascal and 600 degrees Celsius. I will get the enthalpy H11 equal to 3674.9. 3674.9. State point 12 will be having the same entropy. So just like the previous case, S11 will be equal to S12. We calculate the S11, calculate S11. So S11 will be equal to S12, and corresponding to that uh, entropy of S12 and the pressure of 4 megapascal. The pressure of 0.5 megapascal will be getting the H12 will be equal to 3014.8 kilojoule per kilogram. And state point 13 will be the last point where S13 will be same as that of S11, and the whole entropy will be the same. S11, S12, S13 will be same, and corresponding to 10 kilopascal we'll find and 10 kilopascal. You have to actually find the quality of the steam. So H13, but correspondingly, we do not know that right now what will be the entropy of the point state point 1 and the quality of the steam. So I can straight away give that using X will be equal to S11 minus SF divided by SFG, and using that we'll get the enthalpy as well. So H11 minus HF by HFG at 10 kilopascal we'll get H11. So H11 I can straight away, sorry, I beg your pardon, H13. H13 will be equal to 2335.7 kilojoule per kilogram. So this is the starting point. This I have just rushed through this because this follows the same approach as to the previous problem. Now we'll come to the most important part: the energy balance in the closed part of closed feed water heater, open feed water heater, and the mixing chamber. So three energy balance, and we'll get the corresponding the fraction of the steam that is extracted, as well as the enthalpy at the point 8. So we need Y, Z, and H8. These two are the unknowns from this case. So Y, Z, and H8 are the unknowns. So based on three energy balances, we can get it straight away. So the first energy balance is energy balance in the closed feed water heater. That is a top feed water heater. So that comprises only of the fraction of the steam Y. So what you could see is that here fraction of the steam Y into H10 plus Y into H10 plus 1 minus Y fraction of the steam into H4 will be equal to it would be leaving at 0.8. I beg your pardon, it will be leaving at 0.5. So 1 minus y into H5 plus y into H6. So these two combine together to give us the particular points enthalpy, the fraction of the steam y. and that is a closed feed water heater. So once we know why, we can move to the open feed water heater. Just like the previous case of this one closed feed water heater, the open feed water heater's energy balance. So here the energy balance and mass balance, total fluid will be mixing together. So set into H12, set into H12 plus 1 minus Y into set into 2 H2 will give us 1 minus Y into H3. So we all know the other enthalpies, and we can calculate we already know Y from the closed feed water heater, so we can calculate Z from here. So these two are we get all these two, then we can move into the mixing chamber and we'll get the value of enthalpy of it. So basically, Y into H10 plus 1 minus Y into H4 will give us 1 minus Y into H5 plus Y into H6. So here Y is equal to H5 minus H4 divided by H10 minus H6 plus H5 minus H4. Just substitute the values that we have seen in the previous case. So we'll get the value of fraction Y as 1.1766. Similarly, we have to look into the second part. So once we got Y, we have to get the part fraction of the steam X in the open feed water heater. So we go from the top down approach. So saying E in equal to E out, here the mixing happens, set into H12 plus 1 minus Y into Z into H2 is equal to 1 minus Y into H3. So therefore Z is equal to, substitute the values and we'll get 0.1306. So energy balance in the open feed water heater and closed feed water heater gives us Y and Z, the fractions. Now we move to the mixing chamber. So basically, fraction of the steam, the total steam that enters a boiler, that is 1 into H8, will be equal to Y into H7 into 1 minus Y into H5. H8 is equal to 1 minus Y into H5 plus Y into H7. Substitute the values and we'll get H8 is equal to 1 minus 0.1766 multiplied by 1087.4 plus 0.1766 into 1101.2. So that will be equal to 1089.8 kilojoule per kilogram. So H8 will get as well. So basically we got all the three unknowns, the Y, Z, and the enthalpy at the state point 8. So once we get it, we can actually calculate the thermal efficiency straight away. That is equal to 1 minus Q out divided by Q in. So very straightforward thing. So just like the previous case, Q out will be equal to 1 minus Y minus Z. So it's different from the previous case. Obviously, Z is also there. In H13 minus H1. So we'll get it around 1485 kilojoule per kilogram. And then Q input will be equal to there are multiple heat inputs. One is in the boiler, and the second one is boiler will be H9 minus H8 plus a reheat part, that is 1 minus 1 into H11 minus H10. So we already know the values of these enthalpies. We have already calculated, and substituting it, we will get to be around 29 kilojoule per kilogram. So substituting it, the thermal efficiency will be equal to 1 minus 1485.3 divided by 2921.4. The efficiency will be equal to 49.2%. So compared to the previous case, where we have used only the open feed water heater, this is having some difference. We are having a closed feed water heater as well as a mixing chamber in this case, and we got an efficiency of 49.2 operating between the same temperature limits. In the previous case, it was 46.3. So the addition of this reheat as well as a open feed water heater had improved the efficiency straight away. That completes the set of problems I have for this week. So we have seen a few multiple choice questions and numericals based on regenerative reheat cycle. We'll meet next week at the same time. We'll look into a few further problems of second law analysis of steam power cycle. And if you have any problems, you can post it in the course forum that is available in the website. Thank you.